Howdy. This video is on wave particle duality of really small things. Really small things like atoms and light behave very differently than large things like apples. To understand the large things, we have to be able to understand the small things. Wave particle duality is the best example of how really small things act strangely. After watching this video, you should be able to describe how light, electrons, and atoms do not behave like apples. You should be able to describe how photons, which are particles of light, have no mass, no charge, but do have linear and angular momenta. You should be able to describe the particle and wave properties of light, electrons, and atoms. A question that's baffled scientists for a number of years is electromagnetic radiation, light, composed of particles or waves? Historically, it's kind of interesting. Sometimes people thought particles and sometimes waves. And the reason for that is that some experiments you have to use particles to explain, and for some experiments you have to assume light is composed of waves. I'd argue that electromagnetic radiation is composed of neither particles or waves. It's something else that we've yet been able to imagine. But again, wave particle duality just means that sometimes it seems like particles and sometimes it seems like waves. But again, I would argue it's actually neither. Now, if we want to think about waves, one common way is to think about water. And so here we have a water trough, and have a wave generator, and we see that as the waves go through the opening, they spread out. And so this is a property of waves. Now, if you thought that electromagnetic radiation was composed of waves, one thing you have to answer is waves of what? Now, if we had two slits open in our border there, notice that it's like producing two sets of waves. Now, when the peaks of the waves match, that gives us constructive interference. And so the dashed lines correspond to where we have constructive interference, where the peaks of the waves match up. However, the peaks of the waves do not match up, we have destructive interference. And so that would be between those dashed lines. And so you can also picture it this way. And so on the top, the waves are in phase, and so their peaks match up. And so you get constructive interference, and the waves get bigger. Now, the bottom one, it's 180 degrees out of phase of each other, and so the peaks do not match up, and you get destructive interference. And so this is properties of waves. Now, the photoelectric effect is one of three experiments that could not be explained in 1900 by classical methods. The basic idea behind the photoelectric effect is that you shine light, electromagnetic radiation, say ultraviolet radiation, on a metal, and you can kick out some electrons. Now, if you try to explain this classically, you'd assume that the higher the intensity, the more energy the electrons would have that you kicked out. But that is not observed. And so you cannot explain this experiment by assuming that light's composed of waves. You have to actually assume that light's composed of particles.
When an electrode in an evacuated tube, as shown here, is coated with an active metal, electrons may be emitted from the metal when it is irradiated by light. This effect is called the photoelectric effect. Einstein explained the photoelectric effect by using Planck's concept of light as a stream of photons. When light of long wavelength impinges on the electrode, no electrons are emitted. Einstein proposed that this is so because the individual photons do not have sufficient energy to dislodge an electron from the attractive forces of the metal. Even when the light intensity is increased, there is no emission of electrons and no current flows. When light of shorter wavelength strikes the surface, electrons are emitted and are drawn to the anode. Thus, a current is seen to flow. Einstein proposed that the photons of shorter wavelength light impart sufficient energy to the electrons to enable them to escape from the metal. The kinetic energy of the electrons is the excess of that which they require to escape from the metal. When the intensity of the shorter wavelength light is increased, more electrons are emitted, and the observed current increases. However, the excess energy which the electrons possess remains the same. A higher intensity of light increases the number of electrons emitted, so the current increases. However, because each photon still imparts the same energy to each electron, the kinetic energies of the electrons remain the same. When light of still shorter wavelength is employed, the electrons are emitted from the metal with higher kinetic energy. This is so because the higher energy photons have imparted more energy to the electrons, and more kinetic energy remains after.
And so only photons of high enough energy, high enough frequency are actually able to cause the electrons to be ejected by the metal. And so again, if you thought about this classically, you thought about electromagnetic radiation being composed of waves, the higher the intensity, the higher the energy. And so you'd expect that the higher the intensity, the more energy of the electrons. And that's not what's found. And so we see four waves, they have the same frequency, same wavelength, their intensities are different, but no matter how much you increase the intensity, you're not ejecting any electrons. And so you cannot think about light in terms of waves to actually explain this experiment. Now, the blue light has a higher frequency than the red light, and so you actually do eject electrons with low Ke, which is kinetic energy. The red one does not eject any electrons. And now the magenta one, it has a higher frequency, so it's going to be higher energy in terms of per photon. And so you're going to eject electrons with a higher kinetic energy. And so to explain this experiment, you have to treat light as particles, as photons. And so the kinetic energy of the ejected electron depends linearly on the energy of the incoming photon. And so you think about conservation of energy, the energy of the incoming photon is going to be equal to the kinetic energy of the ejected electron plus energy required to remove the electron. And now if we just subtract the energy required to move the electron, we get that the kinetic energy of the ejected electron is equal to the energy of the incoming photon minus the energy required to remove the electron. The energy required to remove the electron is typically called a work function, and it actually depends on what type of metal you're looking at. And so it was Einstein who was able to explain this experiment by assuming light was composed of particles. Now, initially, Planck had postulated that energy was absorbed and emitted in quantized amounts to explain blackbody radiation, another experiment that could not be explained using classical ideas. Einstein extended this and said that energy itself was actually quantized. And he used that to explain the photoelectric effect. And that's actually what he won his Nobel Prize for, was the photoelectric effect. And so he came up with the energy of a single photon was equal to Planck's constant times frequency. Now it's kind of interesting, if you actually look at that equation, you have E as energy of a photon, a particle, is equal to Planck's constant, which is 6.626 times 10 minus 34th joules seconds, times frequency, which would seem to be a property of wave. And so I'd argue that even in just that simple equation, you have wave-particle duality. And so electromagnetic radiation behaves sometimes as it is composed of waves. It has no mass. Sometimes it seems to behave as if it composed of particles. It has linear momentum, it has angular momentum. And so little stuff is really strange. Little stuff behaves much differently than things that we see and touch. And so the atomic level and the microscopic world are very different. We have to think about them very differently. Physicists in the 1900s made the mistake that they assumed that atomic level would follow the same laws as macroscopic level. They assumed that atoms would behave like apples, and they don't. It's completely different. You can actually use Newtonian physics to describe the macroscopic world very easily, Newtonian physics to describe how apples behave, but you cannot use Newtonian physics to describe the atomic level. We need to use what's referred to as quantum mechanics, because the little stuff is strange. Photons, electrons, atoms do not behave like apples. Now it's kind of interesting, you cannot go from Newtonian physics to quantum mechanics, but you can go from quantum mechanics to Newtonian physics. Now, one of the best experiments to illustrate the strangeness of little stuff and quantum mechanics is the so-called double slit experiment. And so we have a source, we have a barrier with two slits, and we have a detector, and on the far right we'll have an intensity. Now you can imagine that if we have a laser and we have the top slit open, what we'd get would be some sort of Gaussian, a little bit above the middle. And now if we open the bottom slit, keeping the top slit closed, we'd actually get another Gaussian. Now the question is, if we had both slits open, would we expect the thing on the left or the thing on the right? Well, actually what would happen is we would get the thing on the right, depending on the wavelength of the light and the separation between the two slits. But we'd get a diffraction pattern. And so that would seem to indicate that light was behaving as if composed of waves. Now we can assume that maybe the light is interfering you have light interfering. And so what would happen if we do exactly the same experiment, but we lower the power of the laser, so we're doing one photon at a time? Would we get the thing on the left or the thing on the right? Now if we're doing one photon at a time, how would the light interfere with itself? Well, what happens is you actually do get an interference pattern. And so even a single photon at a time, it would seem that light is behaving like a wave. And this experiment was actually done. I think it was published in Nature. And it's really kind of cool. You see that you get a diffraction pattern. Now, if you look at the data, it's really kind of cool. So on the left, you have the initial, and then more dots collected, and more dots collected. And so each time a photon hit the screen, it becomes a particle. And so it seems like the light's behaving like a wave from from the source to the detector. But once it hits the detector, it's actually behaving like a particle again. Now we can ask ourselves, what happens if we shoot electrons at the two slits? Will we get the thing on the left, or will we get the thing on the right? Well, surprisingly, depending on the speed of electrons and the distance between the slits, we'd actually get the thing on the right. And so even matter has wave-like properties. Electrons can exhibit wave-like properties.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biprism, thus creating a uniform distribution without any interference when accumulated. Under such condition, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
But really, really cool experiment. So what they did is they took an electron microscope, they put a barrier with two slits on it, and then they measure it. And they shot the electrons one at a time. And so the electron there's no two electrons, and so you can't imagine electrons interfering with itself. But what you're seeing is that at the end, you have a diffraction pattern. But you also saw that the diffraction pattern is composed of single dots. And so as soon as the electron hits the screen, it becomes a particle. But to have the diffraction pattern, it means that from the source of the electrons to the screen, it must have behaved like a wave. And so in the double slit experiment, it seems like it's behaving like a wave at one part and behaving like a particle at another part. We can also ask ourselves, okay, what if we shoot some C60 molecules at a slit? C60 is really pretty big, 60 carbon atoms. Well, actually what happens is, again, we can get a double slit experiment. Again, this was done, it was published in Nature. There's the citation, 1999, Nature 401, page 680 to 682. And here's the data. And so the top one is with slits, the bottom is without slits. And so again, you see the constructive interference, destructive interference. And so even C60 has wave-like properties, even something as large as C60. Now this experiment was done with neutrons, it was done with helium atoms. What if we do it with bullets? So say I take an AK-47 and I shoot them at my slit. Will I get the thing on the left or the thing on the right? Well, I'll get the thing on the left Bullets are actually too massive, too slow to actually have observable wave-like properties. And so the wave-like properties for matter is constrained to just little stuff. Photons, electrons, atoms, molecules are really small stuff behaves really strangely. Bullets are not small enough. They do not behave strangely.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Really kind of cool. And so the act of observation, like he said, collapses the wave function. It's the same with the detector. Once the electron hits the detector, behaves like a particle. Well, if you try to detect which slit the electron goes through, the act of detecting it makes it behave like a particle. And so between the source and the screen, the electrons behave like a wave. They are in a superposition of states. That's how it can interfere with itself. Once it hits the screen, the detector, it has to behave like a particle. That's why we get a specific dot on the screen. And so in the double slit experiment, electrons are behaving both like waves and like particles, but are actually probably neither. The double slit experiment is really important. It was summarized by Richard Feynman, who said a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. Double slit experiment is important to realize just how strange little stuff is. And so there's actually a couple references for some double slit experiments. And so you can do it again. It's been done on electrons, single electrons, neutrons, helium atoms, C60, sodium Bose-Einstein condensates. So is matter composed of particles or waves? Again, I would say neither. Same with light, neither particles nor waves. Some experiments, it seems as if waves. Some experiments, it seems as if particles. Actually, in the double slit experiment, it seems like as part waves in one part and particles in another part. And so aparticle duality of matter means that matter at the atomic level exhibits both characteristics of both waves and particles, but again, probably neither. I hope that was helpful. Enjoy chemistry.